We will set up 4 different configurations, using 4 different ESP boards in combination with 3 different sensors. We will integrate all setups into Home Assistant to be able to visualize the data in Grafana. Additionally, the sensors of all these battery-powered setups are placed in the same house plant. The measured values are logged in Home Assistant and will be compared over the next months. In this video, I would like to talk a little bit about one of my current projects that I'm working on. It is about soil moisture sensors. I would like to use these sensors to measure the moisture content in different places in the garden outside and then use the readings to control the sprinklers and irrigation. Everything should be integrated into my house automatization, which is based on KNX in combination with Home Assistant. The ultimate goal is to build a wireless sensor powered by battery, which provides the moisture and the battery voltage values in certain time intervals to Home Assistant. In Home Assistant, some logic should be used to control the valves, which in turn are connected to a KNX actor. Of course, there are already solutions on the market, for example that one of Gardena. They offer a soil moisture sensor ready to use in their ecosystem. Although all of my components are installed in my garden last fall, such as pipes, sprinklers, irrigation pipes and valves come from Gardena, I will not be using any of Gardena's control units. The reason for this is that I don't want an isolated solution. As the moisture sensors offered by Gardena are linked to their control units, I want to build my own sensor. Alright, soil moisture sensors for Home Assistant. If you do a quick Google search, this seems to be a relatively simple topic. You can order a variety of sensors on Amazon for a few bucks. And in no time the whole thing runs via the ESPHome integration in Home Assistant. That's exactly what I thought when I first looked into the topic 6 months ago. Unfortunately, with what I would like to have, it's not that easy. Why? There are various sensors that differ in both functionality and quality. It is not so easy to find the best sensor. And since we ultimately want to have a battery-powered solution, energy consumption of the complete setup is essential too. We neither want a 10 Ah battery, nor do we want to change or charge the battery every 2 weeks. The status of the project. The device isn't ready yet and it will take some time. But I have selected the 2 essential components. Together we now go through this process in detail. So that is the first part of a longer video series. The 2 components that I'm talking about are the actual soil moisture sensor and the ESP board. Okay, step by step. I have divided the video into the following chapters. First, pre-selecting soil moisture sensors for the comparison test. Second, selection of ESP boards. Third, preparing the hardware. And fourth, integration into Home Assistant and visualization of the data in Grafana. Okay, let's get started. Pre-selecting soil moisture sensors for the comparison test. Basically, there are 2 common types of soil moisture sensors: resistive soil moisture sensors and capacitive soil moisture sensors. We will only test capacitive sensors in our setups. Resistive soil moisture sensors are cheaper, but they have many disadvantages, such as a short lifespan and a strong dependence on temperature and salinity. There is a very good video from Andreas Spiess about this topic. You find the link in the video description below. We are also only interested in sensors that determine the moisture value based on a change in capacitance. Let us search for such sensors on Amazon. Nice, 5 pieces for €8. That's awesome. Nope, it's not. The reason? There are so many different manufacturers for this sensor, and most of them are faulty. According to the YouTuber Flaura Smart Plant Top, 82% of the devices are just garbage. He has a really good video where he explains the individual problems in detail, which are also linked in the video description, and I highly recommend it. Therefore I ordered my sensors at PiHut. I trust this store and expected working sensors with no problems. I also added the soil moisture sensors from ESPHome. Especially their version 2 looked very promising. The sensor is much bigger and it is weather sealed. So these are the 3 sensor types that we are going to use in our test setups. The capacitive soil moisture sensor from PiHut, which does not have any of these common issues mentioned before. The ESPHome Soil Moisture Sensor version 1 and the ESPHome Soil Moisture Sensor version 2. As the version 2 from ESPHRobot is the most promising one, this type will be used in 2 setups. Let's talk about selecting an ESP board. Before we can select a board, we quickly need to clarify what we need. The soil moisture sensors output the measured value analog as voltage. Of course, we also like to monitor the battery voltage. That means the board should offer 2 ADCs. And the sensor should be battery driven. Therefore, boards which already have an according LiPo connector and controller are preferred. There are a bunch of options available on the market which fulfill these requirements. But there is a further parameter which we need to consider: power consumption. And that is also the reason why we are going to compare several ESP boards with each other in this video, because the boards have different energy consumptions in deep sleep. And as we will discover, the difference is truly remarkable. The first board for our comparison is already a few years old, the SparkFun ESP32 Thing. The second one is a relatively cheap board from Amazon, the Asset Delivery ESP32 DevKit version 4. And then we have 2 more expensive boards from ESPHRobot, the FireBeetle ESP8266 and the FireBeetle ESP32 version 4. If you are familiar with these boards, you may know that the FireBeetle ESP8266 board only has a single ADC, and the board from Asset Delivery has no LiPo controller. Therefore, we will add an extra device to each of these setups, but more on that in the next chapter. Now we are preparing the hardware. Before we start, you find links for all the boards and components in the description below. Let's start with the SparkFun ESP32 Thing. We would like to power the sensor directly with 3.3 volts from the ESP board. Let's check the product page on SparkFun if this is suitable. Here is the required info. The 3.3 volt regulator on the ESP32 Thing can reliably supply up to 600 milliamps. According to the info on several websites, the average power consumption of the sensor should be approx 5 mA. Therefore, the sensor can be powered directly via the board without any problems. We are going to read the moisture value on pin 38. The ESP32 Thing is already equipped with a battery connector and a LiPo charger. To be able to read the LiPo voltage, I added a voltage divider on the backside of the board. I will not explain the voltage divider in detail here, as the video is already very long. But in a few words, I added 2 available resistors to scale down the battery voltage by factor 0.55. The max voltage value on pin 36 can then be 2.3 volts. Unfortunately, I didn't have any larger resistors on hand that would reduce the current. The FireBeetle ESP32 board will be used in combination with the ESPHRobot Soil Moisture Sensor version 2. Again, the sensor is powered with 3.3 volt directly from the board. This sensor has 4 wires as the cable is shielded. I cut off the connectors and connected shield directly to ground. The signal pin of the moisture sensor is connected to IO34. Please don't be surprised that I connected the ground cable to this wire end sleeve. This will be used in a follow-up video. For now, to not create a short circuit, I attached a Vago terminal. This board is also equipped with a LiPo charger. To be able to read the battery voltage, the pads for R10 and R11 must be bridged. We find this information in the schematics. If we do so, an onboard voltage divider halves the battery voltage, which is then available on ADC pin A0. Next, have a look at the ESP32 DevKit version 4 from Asset Delivery. We also supply the soil moisture sensor with 3.3 volt directly from the board. We read the moisture value on pin 35. Compared to the other 2 ESP32 boards, this board has no LiPo charger. Therefore, we use the D1 mini battery shield from Amazon. The battery is connected to the shield and the 5 volt output is used to power the board. To be able to read the battery voltage, we again add the same voltage divider as before and measure the value on pin 34. And then there is one more thing. I removed this resistor, which is in series with the enable LED. This LED is on when the board is powered. For us, the LED would simply be a useless energy consumer. Let us come to the last board, the Firebeetle ESP3266. As mentioned, this board just offers one ADC, which we will use to read the voltage value from the soil moisture sensor. Again, the sensor is powered with 3.3 volt directly from the board, and again, shield is connected to ground. Now the question is, how do we read the battery voltage? Therefore, we are going to use another board, the INA3221. The main purpose of this board is current sensing, but it also provides the bus voltage for each channel which we are going to use. The measured value is provided digital via I2C. This board is overkill for what we need, but we will use the full functionality in another video. Without going into details, for now this is our voltage sensor for the battery. The board itself is connected via 4 cables with the ESP8266 port, 2 for power supply and 2 for I2C bus. And to measure the battery voltage, we directly connect to the minus pin on channel 1. We do not need a voltage divider, as the voltage range of the ENA board can be up to 26 volts. One thing I should mention, I unsoldered these 2 resistors for these 2 LEDs, as they would be always on if the device is powered. Again, just useless energy consumers for our purpose. I know that was pretty quick and some people might have wanted more detailed explanations, but I don't want to make the video unnecessarily long. If I missed something important or if there are any questions concerning the hardware setup, please let me know in the comments. The last chapter for today: integration into Home Assistant and visualization of the data in Grafana. Very briefly, I'm running Home Assistant operation system on a Raspberry Pi 4 in combination with an NVMe drive. ESPHome is set up and Grafana with Influx database is also running. I will not cover the setup of these things. If you have any questions about that, guess what? Just leave a comment. Alright, before we flash our sensors, we are going to add a helper button in Home Assistant. This button is later used to enable and disable deep sleep on our microcontrollers. Normally, we want them to stay in deep sleep as much as possible. But if you like to update them later over the air, it's maybe not that easy to catch the window where the device is not in deep sleep. The helper button then can be used to prevent deep sleep for the duration till the update is flashed. Fine, let us prepare the first microcontroller, the SparkFun ESP32 Thing. I will go quickly through the adoption process before we move on to the actual configuration. We go to our ESPHome integration, click New Device, and then we choose the option Open ESPHome Web. Now we connect our board via cable to our PC. Let's click Connect, select the according COM port for our device and press Connect. Then press Prepare for first use and install. This now takes a few minutes. After the device has been flashed, we choose Connect to Wi-Fi and select the SSID and the password for our Wi-Fi network. If you now switch back to Home Assistant, the new device should be discovered automatically. If not, just wait a few minutes or restart the kernel. Press Adopt and enter name for the device. I name it SMS for Soil Moisture Sensor ESP32 Thing. In the next pop-up, we press Install to flash the device again. Once the setup is completed, we can close the window and start to edit our configuration file. After adding the boards, let's go through the configurations. I will not cover every configuration file in detail, only the first one. In the other configurations, we just look at the differences. You can find the complete code for all setups on my GitHub repository. The link to it is in the description. Let's start with the configuration file of the SparkFun ESP32 Thing. The first thing I did, I renamed the device and I also set this friendly name. On boot, I set the priority to -100. At this priority, pretty much everything should already be initialized, so it's the last thing after boot that I'm executing. I turn off the PCB LED, we will see in a few seconds what this command does. Then I have a wait condition. I wait till the API is connected. That means at least one host is connected to the device API. Then I send a component update, so the battery voltage, the moisture value, and then I run a script which has the ID deep sleep evaluation. This block is written when you install the configuration the first time, the logger is enabled, also the encryption key. This block is written automatically. When we come to Wi-Fi, I added one line here. I set fast connect to true. That means the device directly connects to the first Wi-Fi network without doing a full scan. The next thing is we enable deep sleep. We also give an ID because we will use this later, and we set the sleep duration to 30 minutes. So this duration is too short because we do not need an update from our soil moisture sensor every 30 minutes. That doesn't make sense. But for testing purpose, we will start with this value. Okay, the next thing we are defining is a switch. The reason is the ESP32 sync board has an onboard LED, and this LED is turned on when the device is powered. So to save energy, we immediately turn off this LED after boot. You can see this here. Switch turn off PCB LED. Alright, the next thing is a binary sensor. This is the helper button that we have defined before in Home Assistant. Here we need to enter the according entity ID. Then we come to our sensors, the two ADC values that we would like to evaluate. We start with the battery voltage, so this is our ID and also our name. The unit is volt, and we read battery voltage on GPIO 36. So this is the pin where we have connected the output of the voltage divider to. The accuracy is 2. The attenuation is 11 dB. That means we use the full range of the ADC. And we also need to add a filter, because remember, with our voltage divider we scale down the battery output voltage by 0.55. Therefore we now need to multiply by 1.82 so that we have the correct value again. The next ADC value is the moisture voltage. Again, the unit is volt, and we read this value on GPIO 38. The attenuation is again 11 dB and the accuracy is also 2. Alright, what does the script? The first thing is we wait 12 seconds. The reason is, if I do not add a delay here, I maybe do not receive the values. So if you have an idea why, please let me know in the comments. Many thanks in advance. After 12 seconds, we send an update of the battery voltage and the moisture voltage, and then we have these if conditions. So basically we check if deep sleep is prevented. If the helper value is true, then deep sleep is disabled. I send again the battery voltage, I send again the moisture voltage, then I wait 2 seconds, and then I execute the script again. If deep sleep is not prevented, I also send an update of battery voltage and moisture voltage. I wait 3 seconds to give time to deliver the values, and then I enter the deep sleep again. And that's it. We continue with the DF Robot Firebeetle ESP32 board. Everything is exactly the same as in the last configuration file. We do not need this PCB LED switch here, as this board has no onboard LED. The setup for the battery voltage is a little bit different. So first of all, the pin, we read the value on GPIO 36, and we need to change the multiplier to 2, because remember, this board has an onboard voltage divider which halves the battery voltage. We read the moisture value on GPIO pin 35. The rest of the configuration file is equal to the last one. The next configuration file is for the AZ Delivery ESP32 board. On this board we read the battery voltage on GPIO pin 34. The multiplier here is again 1.82 because we have added our custom voltage divider to the battery shield. The moisture value is read on GPIO 35, and our deep sleep script is again exactly the same as before. Now the configuration file for the last board, the Firebeetle ESP8266 from DF Robot. The first sections are equal to the other configuration files. Here we have the first thing that is different. We initialize our I2C communication, therefore we need to define the pins, and we also give an ID. The next thing is the sensor. The soil moisture voltage is read on pin A0. This board has an onboard voltage divider, so we need to multiply the value by 3.2. You find this information in the documentation of the board. And then we introduce our INA3221 board. The I2C address is this value. We find this information in the datasheet from the chip. So then our I2C ID is E1. This is what we have defined here. And then we need to define what we like to read. In our case, from channel 1, the bus voltage. Our script that we execute is basically the same as before. The only difference is that we have some additional logging output here. Alright, so these are the setups for our 4 different boards. Again, you find all the files on my GitHub repository. Just check the link in the video description. Now we come to the best part. We start the comparison measurement. I place the sensors in my room plant, which is a cypergrass. This plant cannot be watered too much. We make sure that we stick to the insertion depths of the sensors as closely as possible to the markings. Well, that looks good. To power our setups, I ordered 4 brand new batteries so that we have as equal conditions as possible. Of course, I have fully charged them before we put the sensors into operation. Now back to the PC. Our devices should have delivered the first values. Let's check in the ESP32 integration the according entities. That looks good. One thing that I recommend is renaming your entities. Therefore, click on the according sensor attribute, then click config and change the entity ID to a unique name that fits for you. This helps later when we search for the values in Grafana. That's also the keyword, Grafana. Let's jump into it. I really love this integration. For example, I use it to visualize the data from my heat pump and from my solar panels. However, we now want to compare our soil moisture sensors. To do so, I simply add a new visualization to my dashboard. Let's call this Soil Moisture Sensors. Alright, now we are configuring the first query. Our source is default and the value is of type voltage. We want to select an entity ID, and the ID is the soil moisture sensor from asset delivery, the battery voltage. And in the section group by, we select fill previews. So we have a continuous line in our graph. And we enter an alias name for the query. In our case, asset D battery. Nice. Let's repeat these steps for the other measurements. Okay, fine. Now we add a label to our y-axis. This is voltage. Then we also can change the unit here. Also the voltage. And the last thing, to visually separate the battery voltage readings from the moisture values, we override some fields. The first field name that we are going to override is the AZD soil. And we like to change the line style to dots and the line width to 2. Let's also do this for the other 3 moisture values. So now it looks much better and more clear. That's it. Now we have to wait a few days to see how our sensors perform. I should clarify one thing right away. The batteries will be used up in just 4 to 5 days. Why? The energy required of our capacitive sensor units is very high. Remember, 5 milliamps. And we also update the values quite often. Therefore, in the next episode we will have a detailed look at the ENA3221 chip. The board which you already have seen in this video will be used to measure the individual power consumptions of the ESP boards and the sensors over time. And of course we will try to extend the battery life. I have nothing more to say except thanks for watching. If you liked it, I would be happy about a thumbs up or a comment. See you next time, and in the meanwhile, happy making.